Hi everyone, I'm Phoebe. I'll be presenting my final year project on image quality assessment and how it can help us in computer vision. There are many applications of computer vision today, such as in self-driving cars and CCTV surveillance. We depend on these systems to make good decisions. However, they might not work well on low-quality images. This can be dangerous in high-stakes scenarios. That's where image quality assessment, or IQA, comes in handy. To illustrate IQA, we will do a simple API demo. First, I'll upload a high-quality image of NTU to the web server. I click on Submit, and as expected, the predicted quality score is close to 100. Next, I upload a low-quality image of NTU. This time, the predicted quality is much lower. IQA allows us to automatically predict the quality of an image. Quality is measured in terms of the mean opinion score given by many human viewers. The range of possible scores depends on the survey method. So how does IQA actually work? In recent years, convolutional neural networks, or CNNs, have been used to perform IQA. The CNNs are often trained and evaluated on artificially distorted image datasets. On the slide, we see some images from one of these datasets. The image in the top left is the original high-quality image, known as a reference. Then, Gaussian noise is increasingly applied to the image, and the mean opinion score goes down. So, IQA models learn to associate the distortion features with the decline in quality scores. However, artificially distorted images are not the same as authentically distorted images. We shall call these AR and AU for short. In AU images, the distortions are due to factors like environmental conditions, the type of camera, and the actions of the photographer. These do not follow the ideal distortion model that is generated by computers. We identify two gaps in research. First, by training on just one AR dataset at a time, existing IQA models may not generalize well. In the real world, images can come from all kinds of domains and are authentically distorted. Second, there are few studies about the effect of image quality on object detection. IQA can play a big part in addressing this gap. We will address these research gaps by first comparing various existing IQA models in terms of their generalizability to a wide range of image domains. Then, we will use IQA to study the relationship between image quality and object detection performance. A key constraint we face is that the widely used IQA datasets are very small. That's because it's hard to get human participants to rate so many images. Therefore, in choosing which models to implement, we made sure that the models have adaptations to learn on small datasets. The first model is Rank IQA. During pre-training, Rank IQA only needs to rank the images rather than regress their quality scores. This means we are not limited by the small number of ground truth scores available. The second model, DeepBIQ, carries out data augmentation by breaking each image into multiple patches. Finally, DeepBIQ involves support vector regression, which is less likely than CNNs to overfit on small datasets. To train and evaluate these models, we used both AR images and AU images. This allows us to cover a wide range of image contents and distortions. The model performance is measured by linear correlation and rank correlation. We aim for scores closer to +1 since this indicates a stronger correlation between the predicted and ground truth quality scores. These are the results. From the table, DeepBIQ shows the highest correlation score. On the right is the plot of the predictions against the ground truths. We can see a strong linear correlation. This model has a 15% improvement over the control model. In this study, the mixed dataset training approach contributes substantially to the good performance. The models do not generalize well when trained on only a single dataset, as is done in most existing literature. We show this in the table on the right, where there is a low SROCC and PLCC. Therefore, we chose to focus on the best model trained using the mixed dataset approach, which is DeepBIQ. Here, we see some of the predictions from DeepBIQ. The images are arranged in order of ascending ground truth quality score. For example, the leftmost image is the lowest quality image of the whole dataset, both in terms of the ground truth and in terms of the predictions. In the next image, we make a similar observation, where the prediction and the ground truth are both around the 25th percentile. Other than the accuracy, we can also consider the model precision. DeepBIQ is precise because it mimics the average human viewer. Meanwhile, different human viewers often give a wide range of quality scores to the same image. Next, we evaluated the model on a completely new dataset. For this, we took two different videos from online. One is filmed at night, and the other is filmed during the day. As expected, the nighttime scenes have a much lower predicted score than the daytime scenes. The predicted scores are lower for scenes with motion blur or bright spots. This shows that DeepBIQ performs as expected on new image domains. So what causes this high performance? Let's look at how DeepBIQ works. In the first step, each image is broken into many patches. The patch features are extracted by a CNN. Then, the features are regressed to a quality score by a support vector regressor, or SVR. The use of a CNN allows us to learn on rich image features, while the use of an SVR reduces the risk of overfitting. Thus, DeepBIQ may generalize better compared to other models which are based on CNNs only. Now that we have found a suitable IQA model, we will use DeepBIQ to study the effect of quality on object detection performance. The performance is measured by the mean average precision, known as MAP. 5 different object detectors were used to get the mean MAP of each image. For AR images, the correlation between mean MAP and predicted quality is very high, as shown by the SROCC and PLCC. For example, in the zebra images, we see that both the predicted quality and the MAP decrease as more Gaussian blurring is added. For AU images, however, the correlation is not as strong. This is because the image content is not being held constant. MAP can be affected by many factors other than quality, such as the number of objects and the size of objects. There is still a positive correlation between MAP and quality though, up to a certain threshold quality. This is possibly because the detectors are pre-trained on ImageNet and hence robust against some level of quality distortions. In conclusion, we implemented several IQA models and showed that they can perform well on AR datasets and AU datasets at the same time. We also showed that the model can generalize to new domains of images not seen before. This contrasts with most of the existing literature, where only a single dataset is used for testing. Next, we make recommendations for IQA training, with weekly supervised learning and regularization. Lastly, we are one of the first studies that use IQA to analyze the effect of quality on object detection. These findings are relevant when designing object detection systems. Thank you for watching.